Okay, thank you very much. Can you hear me well? Okay. This is a joint work with Fedor Pahomov, and it is related to several, I would put it, trends in logic. Firstly, Pfefferman and Schutter's analysis of predicativity. So it's a kind of work, famous work in the 60s in proof theory that was a sort of next big step after Gensen's analysis of piano arithmetic. Pfefferman and Schutter provided a characterization, so they motivated a formal system which would capture the so-called predicative reasoning, and they analyzed it proof theoretically, determined its proof theoretic ordinal, bounds of probability of transfinite induction, which is now known as the Pfefferman-Schutter ordinal gamma naught, and so on. It was technically rather intricate work. Nevertheless, it was a sort of milestone in the development of proof theory. Then there was a later work by Ulf Schmel on the so-called fine structure relationships between reflection principles. These are, let's say, comparison or trade-off theorems between iterated reflection principles of various logical complexity. This work, one can view it nowadays as a kind of very refined formulation of Gensen analysis of piano arithmetic, kind of most general or refined form to this day. And third influence was a study of so-called satisfaction classes or inductive satisfaction classes by Henryk Kotlarski and by other Ratajczyk and other logicians who were motivated mostly by model theoretic concerns, but proof theoretically it's a study of truth predicates in arithmetic. And generally speaking, this falls from, let's say, my perspective as a kind of a general program of applications of methods of probability logic in mainstream proof theory. In mainstream proof theory such as ordinal analysis. So a major role here, and perhaps what is interesting for philosophers, I would say, would be the use of non-classical logics such as model logic, probability logic, and the associated methods such as Kripke models, for example, or various principles that we know very well for model logics, how they actually can be used as a tool for the study of rather intricate, I would say, questions in traditional proof theory. Okay, so let me start with some prehistory, and that's so-called Turing progressions. So the topic emerged in the 30s after Gödel proved his famous incompleteness theorem, including the second incompleteness theorem, which is stated here in this form. So if okay, no pointer. Anyway, if a Gödelian theory T is consistent, that theory does not prove its own consistency assertion. Now, what is a Gödelian theory T? It's a theory satisfying the assumptions of Gödel's incompleteness theorems. So basically, it's a theory expressive enough to talk about arithmetic, and it should be RE axiomatizable in order for it to be able to be the proof predicate, the probability predicate, to be representable in the language of T itself. Okay, so for a wide class of natural theories T, certainly all theories that appear in this talk, such theories do not prove their own consistency assertions. Natural response to this would be, why don't we add consistency assertion of T to the axioms of T just as another new axiom? The question is, would that theory T plus con T be complete? Could you make the pointer work? The answer is no, because the theory is also Gödelian. It satisfies the same assumptions. And one naturally comes to this continuation of this process into stages. So one obtains a sequence of theories, T0, T1, T2. Each next theory is obtained by adding consistency assertion for the previous theory to the list of all the previous axioms. This is a so-called Turing progression of axiom systems. After omega many stages, we come to this theory, which is a union of all these. And again, the same question emerges. If the theory is consistent, would it be complete? You think so? Oh, yeah. The battery is probably low. Ну да, она, если батареечек нету, замените. Работает, замените батарейки. Okay. So, I have to be next slide. Okay, then of course the answer is no. The theory is Gödelian again, and then we come to the next omega many steps, and so on and so on. So this is the so-called Turing progression. Next slide. And Turing hoped to, having defined all this, Turing hoped to obtain a classification of all true arithmetical sentences according to the stages of this or similar processes. He considered several ways of extending a theory. This is how he put it in his paper of 1939, which was essentially his PhD dissertation written under the supervision of Alonzo Church. We might also expect to obtain an interesting classification of number theoretic theorems according to depth, in quotes. A theorem which is required in ordinal alpha to prove it. Sorry? And now, would be deeper than one which could be proved by the use of an ordinal beta less than alpha. However, this presupposes more than is justified. Now, indeed, this sentence highlighted by me in blue tells that Turing was not satisfied with the outcome of his study because he encountered serious difficulties. Okay. The main difficulty here is known as a canonical ordinal notations problem. The source of this problem is this one. So the orderings. Now, in order to formulate the consistency assertions, the axioms of our theories, T alpha, we need a formula, arithmetical formula representing their probability predicates. This formula is basically, can be seen as encoding an algorithm recognizing the set of axioms of such theories. In other words, and this presupposes, since the axioms are numbered by ordinals, this presupposes that ordinals are also numbered, and in fact they should be recognizable. The ordering of the ordinal notations should be recognizable by an algorithm. Decidable or recursively enumerable at least. Otherwise we cannot even sensibly form the sentence con of T alpha. But once we recognize that the theories T alpha are really determined by ordinal notation or algorithms representing alphas rather than the isomorphism types. So the key word here is dependence, that you might remember from the yesterday's talk. So this is a typical dependence problem. So these theories depend on a particular way the ordering is computed rather than on the isomorphism type of the ordinal. Now, playing with these tricks, Turing and then later Pfefferman and Kreisel, who analyzed the situation in depth, they realized that the whole classification idea breaks down because of this particular aspect of the problem. So one can find intricate definitions of ordinals which would have built-in consistency assertions into them, and that would occur very early on in this ordinal classification. So even at stage omega plus 1, one can prove every true pi1, pi01 sentence, and so on. Turing already suggested a partial way out, so the use of canonical ordinal notations. Now, canonical ordinal notations, seen informally, are just ordinal notations defined, let's say, independently of our formal theories. Typical example is a canonical ordinal notation used by Gensen for the ordinal number epsilon naught. This is the ordinal notations built. These are the Notations are essentially terms built by operations from the constant 0 by the operations plus and omega to the power alpha. Yeah, so these two ordinal operations generate certain number of so these terms denote actually an initial segment of the ordinals known as epsilon naught. So this is a canonical ordinal notation. However, we do not know exactly what is a canonical ordinal notation system in general, so that's a big problem. How to characterize the notion of canonicity of ordinal notation, this is not known. In particular, we do not even have an idea in general how do we obtain these canonical ordinal notations. Okay, so something about the second question will be in this talk, but in general this is still a big issue in proof theory. Now there is a second issue somewhat ignored by Turing. In fact, he made let's say some false conjectures, the falsity of which was later detected by Pfefferman, and it has to deal with the second issue, namely that even if one considers, let's say, arithmetical sentences of complexity pi 0, 2, that's essentially two quantifier formulas, then one can produce such a true formula which will not be provable at any stage of a Turing progression T alpha based on iteration of consistency. This is due to the quantifier complexity level. So all the consistency assertions, they're essentially pi 0, 1, one quantifier formula, and two quantifiers are too complex for this. The remedy to cure this situation there is a good remedy. These are called reflection principles. And so here, reflection principles Rn of t are arithmetical sentences expressing that every sigma n sentence provable in t is true. So they should be seen, in fact, as statements generalizing the usual consistency assertions, sort of relativized consistency assertions. In fact, Rn of t is expressible as a pi n plus 1 sentence, and R0 of t is equivalent to consistency of t. Okay, so dealing with, similar to the consistency assertion, these Rn's, these reflection principles can be iterated in a manner of Turing, and one can consider more general, more complicated progressions obtained from iterating such principles. And finally, related to this, there is another important notion that is needed to state let's say to correctly state the results about these progressions, is a notion of n equivalence of two theories. Two theories are n equivalent if they prove the same pi n plus 1 sentences. So this equivalence of theories is sort of weaker equivalence than the usual deductive equivalence when we say that two theories are equivalent when they prove the same theorems. So this is much weaker, but we say that they're n equivalent if they agree on the pi n consequences. So the bigger n, the closer the theories t and u are to each other. And in terms of this proximity, we can actually measure, we can approximate theories using iterated reflection principles in the sense of this proximity notion. So this is how it works. So this is essentially the setup by Ulf Merl, who considered, sort of formulated this idea of Turing in a workable form. And it is as follows. So let's first fix some basic elementary arithmetic. For us, typically it's a finite fragment of Peano arithmetic where induction is restricted to Kalmar elementary functions, something like that. So it's a very weak theory even compared to PA. Now, starting from that system EA, we can consider various Turing progressions obtained by iterating reflection principles Rn alpha times. So here they are denoted Rn alpha of EA. Now, having generated these stages of reflection principles over some weak theory EA, we can actually hope at a certain stage to obtain a suitable approximation of a given theory EU. So this is called the analysis by iterated reflection. And a typical example was a theorem proved by Schmerl in 1979. So if U is piano arithmetic, the usual one, and we start with elementary arithmetic, and iterate over elementary arithmetic any of these schemata Rn, in fact epsilon naught times, which is not accidental, and then we obtain a theory, this one, which would be n equivalent to PA. It is n equivalent to PA, it means that it proves the same pi n plus 1 sentences. On the other hand, the theory is itself axiomatized by pi n plus 1 sentences, so this is essentially an axiomatization of pi n plus 1 consequences of PA. So this is a very short, understandable formula, shortly put. However, it is very strong in terms of what can one prove using this. So in fact, this result, stated here rather abstractly and in this way, yields practically all proof-theoretical results that we know about piano arithmetic, like a consistency proof by transfinite induction up to epsilon naught. So this follows if one puts here 0 for n. A classification of provably total computable functions. So these hierarchies of fast-growing functions, Paris-Harrington principle, etc. So this can be inferred from this result, putting n equal 1 for functions, and more generally. So this is a powerful and general statement of proof-theoretic results, which is clearly can be seen as a realization of sort of Turing classification program, because yes, using canonical ordinal notations for epsilon naught, but we classify pi 0, n plus 1 consequence of a given theory using this. So this is a kind of results that we want to obtain now for, let's say, more general class of theories. Conclusions for this part of my talk. So basic conclusion is that results of this kind, they provide the finest of the existing classifications, ordinal classifications of, let's say, arithmetical theories, of theories considered in proof theory. They yield all the standard proof-theoretic results, proof-theoretic information about a given theory U, once this result is established. Namely, bounds on consistency strengths, consistency proofs, classification of provably total functions, bounds on provable transfinite induction. This is related to a recent paper by Pahomov and Walsh, who studied this analogs of this in the second order context, where in fact transfinite induction naturally lives in. Okay, now we want to go with this program for the class of predicative theories, theories which go far beyond piano arithmetic. And now we want to in fact apply this to theories of iterated truth predicates. Now the question is, why do we want to consider iterated truth predicates? Of course, this is for us this is interesting and convenient for the following main reasons. So firstly, truth predicates and reflection principles, which play a central role here, they are tightly related. To go on with reflection, one needs to have a truth definition. And once one has a truth definition, natural way to ask is, okay, does reflection hold, and so on. So these are anyway the objects that we would need to consider if we want to study reflection principles. Secondly, theories of iterated truth predicates are mutually interpretable various standards or consider theories of predicative strengths considered before. Theories of ramified analysis, that's a framework of Schutte and Pfefferman, or more modern framework of iterated of second order arithmetic with axioms of iterated arithmetical comprehension, and so on and so on. So here the world of these theories is essentially known to be interpretable with the series of iterated truth predicates. However, our framework, theory with truth predicates, remains first order, which for us is kind of convenient because we know how everything works, how our ingredients, so to say, work for piano arithmetic, so we can sort of take them without any change to theories of truth predicates. Okay. So here are some details. Let's now start from working out this project. And so this was introduction. Now let's see how it develops in practice. So we consider some first order language L extending that of piano arithmetic by finitely many predicate letters. So that's our general language we start with, and then we consider extensions of this language L alpha by alpha many new unary predicate symbols denoted T beta. Of course, these symbols will denote the truth predicates. And a remark here, an important remark, is that, of course, the ordering on alphas should be fixed beforehand. In any way, so far we don't even assume that it is canonical or not. In some elementary way, we have an ordering representing the ordinals. And then once this is fixed, it induces a Gödel numbering of all the objects in our language L alpha. So that's pretty clear. So we want to give the meaning of the formula T alpha of the Gödel number of phi should mean that the formula phi is a true L alpha sentence. Okay. In order for these new symbols to work as intended, we need to postulate certain principles for truth. And here we opt for a rather weak axioms for truth, which is one of the key technical ideas here that allows everything to work. Once we, in this framework, we start really with a theory with very weak axioms for truth, but the stronger axioms for truth will be all inferred by reflection. So the main thrust, so to say, of the axioms will be in reflection, not in truth axioms. So our weak axioms for truth are known as uniform Tarski biconditionals, UTB. So here in this context, we postulate for each predicate T alpha. We predicate this Tarski biconditional phi of x is equivalent to T alpha of phi of x. Nothing more. And this second series of axioms just forbids T alpha to be true on anything which is not a formula. It's a technically convenient, let's say, assumption, but not essential for anything. And then the series UTB less than alpha are defined as the union of all theories UTB beta, or schemata UTB beta for beta less than alpha. So this is our basic, let's say, meaning of symbols T alpha expressed in terms of these axioms. What is known and very easy to see is that the theory UTB alpha is conservative over any of these series UTB less than beta for beta less than alpha, simply because if one takes a model, any model of UTB less than beta, one can expand it to a model of UTB alpha just as one would do. So in fact, consider the truth definition in that model, the usual Tarski, so to say, truth definition in that model, and it would satisfy these biconditionals. You can do it transfinitely, and that's a model theoretic construction. But in fact, it can be also proved constructively or syntactically by producing a local interpretation of one theory in another. So this is not a foundational issue. Simply, these axioms are so weak that we clearly see that they don't prove in themselves, they don't prove anything new about arithmetic or previous stages of this process. Okay. Now let's let's say part of this program is to define appropriate reflection principles, and these are determined by logical complexity levels, which in this language go somewhat beyond the usual arithmetical classes. But still, let's start with the arithmetical hierarchy. So the delta 0 L is a closure of atomic L formulas under conjunction, negation, and bounded quantifiers. So that's the usual bounded formulas. Now, in our basic language, so that's relativized delta 0 formulas. And then the usual arithmetical hierarchy relativized to L. So pi n plus 1 formulas are obtained by a universal closure or universal quantifier over some sigma n, and sigma n plus 1 by existential quantifier over pi n. So this is essentially as it should be. But then we can build the hyper-arithmetical hierarchy using the mechanism of T alphas. So we can, let's say, define these classes pi alpha for ordinals alpha, where if alpha is a finite ordinal, then it's just the usual class pi 1 plus n defined before, that we already defined. And then for limit ordinals and the ordinals that go, let's say, beyond the first infinite, beyond omega, it is defined like this. So we consider the class pi n plus 1, but now relativized not to L itself, but to the language L beta plus 1. Right? So we go to the limit stage, which is closest to our ordinal alpha, and then that will be the definition of our class of formulas. And for limit ordinals, we take the union, so that's pi less than lambda, the notation. So what one obtains is that essentially in the standard model of arithmetic, for example, if one starts with the pure language of arithmetic, then pi alpha formulas define pi 1 of 0 with alpha prime sets in n. So that's essentially hyperarithmetical hierarchy built in the usual way. So in particular, pi less than omega are the usual arithmetical sets, and pi omega is in fact pi 1 in the class of all true arithmetical centers. So it's pi 1 of T0. So, so that means that this indeed, our language has a definition for the classes of the hyperarithmetical hierarchy. And then we go to reflections. So consider any Gödelian theory S containing elementary arithmetic. Let box S denote the probability predicate for S. So box S phi means phi is provable in S. And then we define our reflection. So our alpha is a principle that whenever phi is provable, then phi holds for all phi, formulas phi, in this class pi alpha. So sufficiently high up in this hyperarithmetical hierarchy. And so this alpha can be a limit ordinal, can be a successor ordinal, doesn't matter. And we have these principles less than lambda, where lambda is a limit ordinal. It's just the union of all these schemata are alpha. Okay. As it happens, in our context, these will be finitely axiomatizable schemata, and this will be not. And in fact, our alpha of S can be seen as a statement of consistency of S plus all true sigma alpha sentences. But so far, you can just consider this as intuition rather than a theorem. Okay. Anyway, so we have defined our reflections. Quick summary. Given an elementary well-ordering lambda, we specify the language L lambda. We specify the formula classes pi alpha for alpha less than this ordinal, so hyperarithmetical hierarchy up to omega lambda, essentially. And then we fix the basic theory of iterated Tarski biconditional, which are B. So that's something like EA plus UTB less than lambda, but EA should be extended a little bit. This is just a convenience. Still some very weak extension by truth predicates of something which is substantially weaker than piano. We have the same notion of pi alpha conservativity. Two theories are alpha equivalent if they prove the same pi alpha sentences. So everything now is in place. And now we would like to see what actually, how these R alphas are related to each other, because that's the essential ingredient of this proof theoretic analysis is to understand how different R alpha relate to each other for different alpha. This has to do with finite iterations of these operations. So finitely iterating R alpha finitely many times is just considering the first omega stages of this Turing progression over S. And then we have two basic conservation results. First theorem is this one, that under certain conditions, which will be satisfied, we have this relationship, that alpha plus first reflection over S will be alpha equivalent to alpha reflection over S iterated omega times. So using reflection of the next level of logical complexity, we can prove exactly omega many iterations of the previous reflections, but not more. They will be alpha equivalent to each other. In arithmetic, this is well known and yields some well-known theorems. For example, the so-called Parsons-Mintz-Takeuti theorem on the pi2 conservativity of sigma 1 induction over primitive recursive arithmetic. This is essentially because this sigma 1 induction theory is equivalent to, in our notation, something like R2, and PRA is R1 iterated omega times over EA. But the main idea is that this is a very basic, simple relationship. It does not even involve, so it does not involve any iterations beyond omega. Next result is kind of reduction, similar reduction for limit stages. So if lambda is a limit ordinal, then R lambda of S is equivalent to R less than lambda of S, is conservative over for all alpha which are less than lambda. So it's less than lambda equivalent. And again, this result is, let's say, illustrated by this corollary, which is for the simplest case that lambda is omega. Then we are dealing with, then the left-hand side is essentially this theory. So we consider our basic system IB, and then we consider something like reflection over S for formulas which are pi1 in the truth predicate. The result claims that this theory is simply conservative over the arithmetical system, which is piano arithmetic plus uniform reflection for arithmetical formulas over the system S. So somehow jumping over every limit point, we can, so one can see it in this way, that at limit stages our Tarski biconditionals do not add much strength to our principles, so they are simply stay conservative over the union of everything that was previously obtained. Both of these basic conservation theorems are formalizable in EA+. Kotlarski's work. So in proof theory, in the study of satisfaction classes, perhaps more interesting than these weak axioms for truth are so-called compositional axioms for truth. Compositional axioms for truth are saying that truth commutes with Boolean connectives and with quantifiers, like this. And that this can be stated uniformly for all Gödel numbers of formulas phi and psi. Now, of course, these four axioms for schemata are much stronger than our plain Tarski biconditionals. They appeared in the work of Henryk Kotlarski and Ratajczyk in the late 80s and early 90s. And one of the results was this. Or the result proved by, let's say, ad hoc model theoretic methods was this. If one considers piano arithmetic plus this new truth predicate plus CT axioms, compositional truth axioms, plus induction for bounded formulas over the new truth predicate, then the resulting system will in fact be conservative over the extension of piano arithmetic by omega iterations of the uniform reflection. So it will prove the reflection, uniform reflection for piano arithmetic for arithmetical formulas, reflection over this, and so on, omega many times. So it's a rather strong extension of piano arithmetic. Here, let me just mention that this all follows from our theorems 1 and 2, because Kotlarski series is in fact contained in this one. So UTB plus one reflection over UTB. So this one reflection over UTB allows us to prove, in fact, all these Tarski compositional axioms. And for this theory, we can obtain this conservation results from the previous two above-mentioned theorems. So that's a relation with theories of compositional truth, if you like. Okay. So now we come to the most interesting part of my talk, where these non-classical probability logics start to emerge. Namely, we need to essentially obtain a generalization of these conservation results to transfinite iterations of these relations principles, and to get our notation systems from somewhere. And this is done here in this way. Consider our system IB. Can make sense for, in fact, practically any arithmetical Gödelian theory that you like, but in our case, let it be IB. We can define, on the set of Gödelian theories, we can define the relation less than IB as follows. If we say that S is less than T, if T is contained in S, provably in IB. Provably in IB. So it's the usual containment relation, S contains T, but here we state that it is provable in IB. Then we can consider the associated equivalence. So two theories are IB equivalent if one is less than the other. So this less than IB is a pre-order, and when one factors it out, one obtains a lower semi-lattice with the lower bound of two theories essentially corresponding to their union. Essentially corresponding to their union. This semi-lattice will be our basic field on which we play with our ordinal analysis. So in fact, every reflection principle R alpha defined so far acts as a unary operation on this structure, on GIB, sending every extension of IBS into the theory IB plus this R alpha of S. So that's how these reflection principles are now emerge as algebraic operation, because now we have a structure which is a semi-lattice GIB together with this list, a family of monotone operations. Now the question, of course, is what can we say about this algebraic structure? And in fact, the answer is quite a lot, though it is naturally complicated. What we need is a characterization of the identities of this structure. And that's where probability logic comes in. However, it's a weak form of probability logic because we don't have any logical operations except conjunction. We don't have negation, we don't have disjunction. We have our operation R alpha, which we interpret, we see them as diamond modalities, in fact, here. And then it is called such weak model logic languages are called strictly positive logics. And we have a strictly positive logic called RC lambda, or called reflection calculus, which completely determines the behavior of these operations R alpha for us. That's the list of the principles that we have here. So our formulas, strictly positive formulas, are now built from top, constant through propositional variables, conjunction, and these diamonds written simply as alpha I, alpha A. Principles for implication, for principles for, let's say, we read A turnstile B as, in terms of this lattice, that simply means that A is less than B, less than or equal B. So we have the usual principles, pre-order axioms. We have lower bound axioms for conjunction. We have monotonicity for each R alpha. We have semi-idempotence. So it's 1/2 of idempotence axioms for R alpha. We have the obvious principle that R alpha implies R beta if alpha is bigger than beta. And we have a very, let's say, the most non-trivial but easy to understand principle that R alpha A and R alpha B, together they imply R alpha of A and R beta B. So that's a mixed principle, mixing two different R's reflection principles together, and it's a sort of the vehicle for this calculus. So here is a kind of short derivation using this. So the claim is now that in fact, if A implies B in this calculus, is provable in this calculus, then in the lattice we have the inequality. The corresponding theories are provably the theory A star implies the theory B star. So this, in fact, determines for us completely the behavior of this schemata R alpha. And system RC lambda is enough to yield for us the ordinal notation system. So now this is a little miracle because now we have the ordinals. So we started with certain semi-lattices and algebraic structures which looked familiar from model logical point of view, but now we come to ordinal notations in this way. So consider the natural ordering relation on formulas of RC defined in this way: alpha A is less alpha B if B proves alpha A, if B implies alpha A. So this corresponds to the idea that the theory B proves the alpha reflection over A, something like that, put arithmetically. Now we consider the set W of all variable-free formulas in this calculus. So we're talking about model logic language now. This is strictly positive model logic language. Let W alpha be the restriction of W to the signature with modalities numbered by ordinals greater or equal than alpha. Then the following facts hold. Firstly, every such formula A, variable-free formula, is equivalent to a word. In other words, a formula without conjunction. Why do I call it a word? Because if a formula contains no conjunction, that it is just obtained from constant top by applications of various modalities that we have. So it's a sequence, finite sequence of ordinals, in some sense, a word. Secondly, for each alpha, this structure is a well-ordering modulo the equivalence in this logic, modulo equivalence in RC lambda. So it's a genuine well-ordered structure. In fact, the order type of this structure is quite big. It can be characterized in terms of Veblen function phi. In particular, if one considers just w less than 0 in the logic RC omega to the alpha, then this will be the Veblen ordinal, the ordinal phi alpha of 0. In a moment, I will explain for you what phi alpha is, but let's say, ideologically speaking, I would say that we don't even need to consider these functions phi alpha, because this structure itself, or this structure itself, is already a canonical ordinal notation system. This order relation, less than 0, is defined in terms of probability in our calculus RC lambda. It's this one, this relation between variable free formulas, and of course by standard model logic methods we know that this calculus RC lambda is decidable, complete with respect to Kripke model, so it's very easy in terms of model logic properties, and it is decidability of this relation yields that this is a constructive ordinal notation system. If we want to relate it to, let's say, Pfefferman-Schutte ordinal calculations, then we can do this little work and see that it is expressed in terms of their functions thus. But in principle, we would do without it. Now, what is this phi 0? Phi 0 is obtained by taking fixed points of ordinal functions like this. So we start phi 0 is the omega function, omega to the 1 plus beta. Phi alpha of beta is the bth fixed point of phi alpha, and phi lambda is a simultaneous fixed point of this phi alpha for previous alpha. So gamma naught is the least ordinal, bigger than 0, closed under phi alpha of beta binary Veblen function. And that's exactly the bound to predicative methods by Pfefferman and Schutte. So essentially, considering our ordinal notation systems, we see that they are equivalent to using these algebras is equivalent to using these phi functions in some sense. Okay, and now we come to the result, which is that we wanted to understand. And if we went through everything that is done by now, then the proof of this theorem is something like 1 page, because it is our definition of ordinal is so well related to the definition of Turing progression that what comes out is this. Consider any word alpha, word A in W alpha. So any model logic formula without variables, if you like. Consider its arithmetical interpretation with respect to a given system S. S here, elementary arithmetic, for example. So consider this AS star, which will be a rather strong arithmetical system obtained by combination of several reflection principles whose complexity is determined by the ordinals appearing in A. So A tells us how to apply these reflections. So it's a rather big theory in our language of iterated truth predicates. Now, this formula tells you that this theory is alpha equivalent to operation R alpha iterated over S beta many times, where beta is this ordinal, is the ordinal of our given word A in the well-ordering W alpha that we work with. So here essentially, this formula tells you that in order to see what is the proof theoretic strength of this, you just look at the abstract structure of our algebra, see what is the ordinal, and that will be the answer. A corollary is this kind of relationship, which is formulated here in terms of phi function, which is a trade-off, Schmerl type trade-off relations. If you have a reflection of the form R alpha plus omega to the beta iterated gamma times over S, then this will be equivalent to R alpha operation iterated many more times over S. So that comes out of this little formula. And this, in view of the first part of my talk, once we obtain this, we are sort of free to prove anything, any of the standard proof theoretic characterizations of theories related to these hierarchies of truth predicates. And let's see a couple of examples, and the simplest examples that one can consider here and how it plays out. So, piano arithmetic. This is already the case that was studied 20 years ago. So nothing new here. We obtain the Schmerl relationship. The next interesting case is the theory ACA, so-called arithmetical comprehension. So the second order arithmetic with the principle of comprehension, with full induction and principle of comprehension for arithmetical formulas. What is well known that the theory ACA is mutually interpretable with the extension of PA by one compositional truth predicates T0, which is again equivalent to the theory IB plus this reflection, R less than omega 2 over IB. In order to compute its proof theoretic ordinal or characterize its consequences of particular logical complexity, what we need to do, we need to apply our relationships that we have. And this is how it plays out. So IB plus R omega epsilon 0 of IB is equivalent, less than omega than to IB, and this iteration. So we obtain that ACA is n equivalent to IB plus Rn iterated epsilon naught times over IB. So it comes from, let's say, calculation on the basis of our formula. Of course, this was well known for ACA, I would say. At least in principle, this was well known that the proof theoretic ordinal of ACA is epsilon naught. So this confirms this, but it confirms this in some sense for all arithmetical complexities. Next example, ACA plus. Another theory which appeared in reverse mathematics, for example. So ACA plus is ACA together with the axiom stating that for every set, so it's second order arithmetic ACA as above, plus this axiom saying that for every set there is an omegath jump of this set. Now looking at this closely, it becomes apparent that ACA plus is the same as the extension of piano arithmetic by that many truth predicates. So you have omega plus 1 many truth predicates ending with T omega here. Which again gives you the equivalence with this system, IB plus reflection of that specific ordinal over IB. Looking at this, applying the previous theorem, you calculate that this is omega equivalent to IB plus R omega that many times phi 2 of epsilon 0 of IB. And in other words, this is conservative for arithmetical sentences over piano arithmetic extended by that many times iterated uniform reflection. So, good. One can go further up to theories of significantly stronger theories, but I think I will finish here. Thank you very much.